Hello and welcome to the Glacier Pavilion. My name is it good? Yeah. My name is Thomas Frank. I'm a PhD student at Uppsala University in Sweden. And we're looking forward now to the session on snowpacks, glaciers, and water supply, future projections. I also want to welcome those of you who are sitting at our hubs in Geneva and Stockholm. And I'd like to invite all of you to post questions in the chat if you're in Geneva or Stockholm, or to ask the speakers that are there directly. Also, everybody here, welcome, and you're most welcome to ask questions. I would now like to turn over to Regine Hock, professor at the University of Oslo in Norway and at the University of Alaska in the US.
Thank you very much, and thank you very much for the opportunity to speak here. So I will talk about glaciers today and make the point that every degree warming matters. So I would talk about all glaciers in the world outside the ice sheets. So not the Greenland and Antarctic ice sheet. This is about 200,000 glaciers. They cover an area of 700,000 square kilometers that corresponds to the area of Texas or the area of the United Kingdom and Spain together. And if you melted all these glaciers, the sea level equivalent is about 40 centimeters. These glaciers have lost mass over the last 100 years and decades. Just here an example, or here many examples in the world. So massive glacier losses here in Alaska, here in Patagonia, here in Iceland. Just a few years later, rapidly retreating. So in 13 years, the glacier is no longer visible here around the corner. Or what is really new is that in the last years, in very, very few years, you have massive changes here in Switzerland. In just 8 years, they go back again, massive changes just in a few years. Or another example here from Switzerland is here the Finland Glacier, also within 8 years, massive retreats. If you look at all glaciers in the world, this is your calculations taking all the measurements that we have. And what you see is the thinning rate. Minus 0.5 means 50 centimeters of thinning every single year, averaged over all glaciers in the world. And what you clearly see is there's an increase in thinning and mass loss in the last decades. The last 2 decades have doubled the amount of thinning than the preceding decades. And sort of right now, there's a thinning of about 0.5 meter over all glaciers in the world. 0.5 meter of thinning every single year. This here shows the same type of graph, the thinning rates, the mass losses, but for different regions in the world. So what we see is glaciers lose mass everywhere, but the total amounts and the trends vary. And we see also large interannual variability here. From one year to another is huge changes. But what we see is that in some regions, the mass losses are much less than in other regions. Like here in Arctic Canada, Russian Arctic, or high mountain Asia, there's mass losses of about maybe 10, 20 centimeters per year. Whereas in some regions, like here, Central Europe, Caucasus, or low latitudes, the mass losses in the last decades are about 1 meter or so per year. So why do these glaciers retreat? Air temperature is the main driver, but locally it's other meteorological variables as well. And another interesting aspect is that in a study here calculating the anthropogenic contribution, you see an increase in the anthropogenic contribution from about 25% before 2010 in those more than 100 years, and now up to almost 70% of the retreat and thinning and mass loss of glaciers can be attributed to human impacts. So how will the glaciers change in the future? Here's an example of a study in Switzerland. Here, the largest glacier in the European Alps. And you see massive changes, but very big differences depending on the emission scenario. With the high emission scenario, essentially all the glacier essentially disappears by the end of the century. With a low emission scenario, quite a lot is left over. Another example is here, projection of the Juno Ice Field in Alaska. This is almost 4,000 square kilometers of ice, more than double what there is in Europe, in the European Alps. And also here, by the end of the century, massive changes, retreat of an area and volume loss of about 50 or 60%. What you see here is the results of an international model intercomparison, essentially all the studies that exist and do projections of all glaciers in the world. And here differentiated for different regions. What you see on a global scale, the projected mass losses are about 20 to 40% for depending on the emission scenario. And that corresponds to a cumulative sea level equivalent of about almost 80 millimeters to about 170 millimeters. But also here, huge differences between the regions about the relative mass loss. So number one here means it's 100% mass in 2015. How much is left over every year? And we see that in regions that have a lot of ice, especially the polar regions, the mass losses are about 10, 20% or so, up to 30%. Whereas in regions where there's a little ice and smaller glaciers at the moment, the mass losses are massive. Like here in Scandinavia or Central Europe, low latitudes, for the high emission scenario, it's almost a complete deglaciation projected. So here's a study translating these projections in global temperature increase. And for what you see is here for a scenario for plus 1.5 degrees. And what you see is each dot here is all the glaciers in a grid cell where there is glaciers. Blue is 100% of the mass relative to 2015. And red, white, and the circles with black circles with white means that all the glaciers have disappeared. And sort of yellowish is 50% of the mass is left over by the end of the century. So you see huge spatial variations depending where you are, how much is remaining for a scenario of 1.5 degrees. This is for 2 degrees. This is for 3 degrees, 4 degrees, 5 degrees. So obviously, the more warming you have, you see a lot more red. So massive deglaciation for this very high emission scenario. What you see here is now the global glacier mass change that is projected by 2100 for every degree global warming above pre-industrial. And you see the mass loss in percent, you see the area loss in percent, the sea level rise in millimeters, the number of glaciers lost, and the thinning rate for each of these degrees temperature increase. And what is really fascinating to see is like temperature matters. It's a linear increase. The higher the temperature, the more mass loss, area loss, sea level rise, and so on you have from these glaciers. The thinning rates here for the highest, like 6-degree temperature increase, is up to 6 meters per year, averaged over the entire world. This translates here into sea level projections, also for these temperature increases between 1.5 and 5 degrees that are extracted from the GCMs that drive our glacier models. And what you really see is every single degree makes a difference. It matters. So limiting global warming reduces the glacier contribution to sea level rise. How will the glaciers change beyond 2100? There's not too many studies, but here one sort of an older one, but which nicely illustrates what has been projected, is for a low emission scenario. You see there's an increase in melt, but then if you move on, the contribution here to sea level rise decreases. And it decreases for all the scenarios, but for very different reasons. In here, the high emission scenario is because the glaciers essentially melt away, Whereas for the low emission scenario, that is because the glaciers reach a new equilibrium and survive. So you get the same result, but for different reasons. And in some of the regions, actually, for the low emission scenario, the glaciers start growing back again. So again, every degree temperature increase matters. Another example here, sort of also a projection up to like 4,000 years. And this is the Juno Ice Field that I showed before, where we projected very massive mass changes. But if you keep the climate constant, these are the different trajectories, the ice field stabilizes at about 90%. If you keep the climate that is projected for 2010 to 2040 and so on constant, you stabilize it at a lower level. It is only if you go until the end of the century and keep that climate constant, the high emission scenario, the ice field is gone. But you can really, the ice field stabilizes at very different levels if that projected climate is sort of frozen at some point in time. So again, emission pathway matters. So just a few words about why does glacier wastage matter? What are the impacts? I mentioned already sea level rise several times. The glaciers outside the ice sheets make about 1% of the world's ice volume, but they have contributed in the last decades to sea level rise more than the Antarctic ice sheet and almost as much as the Greenland ice sheet. And roughly about a fourth to 1/3 of the sea level rise comes from the glaciers around the ice sheet in different periods in the past. And what is really interesting when you look at the projections here for a high emission scenario and a low emission scenario here in blue is for the high emission scenario, so the track we are on, the sea level contributions by the end of the century are similar to the current rates of total sea level rise of about 3 millimeters per year. So for the RCP 8.5 here, the sea level contributions just increase and increase with the rate by the end of the century that is the same as the entire sea level rise at the moment. Glacier mass loss affects runoff. And what you typically see is first, when the glacier retreats, an increase in runoff, but then a decrease. And this peak here, we call peak water. And obviously, this is important for water resources management. If the glaciers are still increasing in mass loss, or if the mass loss is increasing, the runoff from the glaciers, or if the runoff is decreasing. This is here a compilation of all studies we could find here for the IPCC SREC report about peak water. And I want to walk you through here. This is for the high emission scenario. Each bar here is, let's go back, each bar shows the area in each region that has reached peak water already. When is peak water reached? Here in different decades over the period 1980 to 2100. And all the bars together for each region are 100% of the area. And the green line here is today. And also, and this is a modeling study, but also there's all kinds of case studies shown here by the circles for comparison. But the more bar area is before today, that means peak water has already been reached in these areas, or in at least part of the areas. Whereas the further in the future, there's more higher bars, that means peak water is reached later. And these are you sorted by peak water, and you see in the regions with little ice, like the low latitudes, Central Europe, Western Canada, a lot of the area in these regions, peak water has already been reached, which means the runoff from the glaciers is decreasing. Whereas in other regions with a lot of ice, like in the Southern Andes or Alaska, runoff is still increasing, and peak water is reached sort of towards the end of the century. So, summarized here. Within each region, there's huge differences between peak water. This is a simulation here for high mountain Asia for the different emission scenarios. And you see it depends very much on the emission scenario, but it also depends where you are. Like here, the monsoon-fed rivers hit peak water before 2000, before the middle of the century, whereas more westerly fed rivers, like the Indus, hit peak water later. So there's huge regional differences within each of these larger glaciarized regions. So it really depends where you are, if the runoff is increasing or if the runoff already is decreasing from the glaciers. And we can here model like the different contributions. It really matters where you are. Everything that is here sort of reddish is water from the glacier melt. And depending where you are, it matters a lot. Like here in the Tarim Basin, most of the water here comes from the glaciers. So if the glaciers disappear, it has a huge impact. Whereas in other basins, like here the Ganges or the Salvan, the glacier contribution is much less. So the importance is not as much as in. So it really depends where we are and how far this decline in meltwater matters or not. The meltwater can also lead to release of contaminants. There's anthropogenic legacy pollutants stored in glacier ice, and they can have possible impacts on the water quality of down glacier streams and ecosystems. The glacier retreat can lead to a reduction in slope stability. Here's an example here from Claridenfjord in Switzerland, where a rockfall occurred after a massive thinning of the glacier. So it can lead to a decreased stability of mountain slopes and to landslides and rockfalls when the glaciers thin and expose that rock. Another impact is hazards. The impact of glacier retreat can be glacier outburst floods. The number and size of lakes will increase as the glaciers retreat. This increases the risk for glacier outburst floods. And those are really the most deadly hazards that can happen. So the most deadly glacier outburst floods occurred here in India with more than 4,000 fatalities. So this is really a major impact if there's more lakes and a higher potential risk for outburst floods. It has an impact, the glacier retreat, on cultural values. Some glaciers are among the principal reasons in 5 sites and in 28 sites the secondary reason for World Heritage inscription. But almost half of these heritage sites could lose their glaciers by 2100. So essentially the reason why they became World Heritage sites may disappear. The retreat of glaciers also impacts cultural values in many areas of the world. They are part of their belief system, and sort of like the retreat of glaciers can have a negative impact on their well-being. So I come here to the end, just want to conclude, and my main conclusion is really this: glacier decline can be slowed by limited warming, and every increment, every single degree temperature index makes a difference. So thank you very much for your attention. I'm happy to take questions. Yeah, I think you.
So one thing I'm wondering is, are there any records of how many glaciers we've actually lost at this point, say over the past decade? I know there's been some in the news and like that. And my very own little glacier, well, it's not mine. Back in 1982, I did work on these 2 little ice caps on northern Ellesmere Island, did mass balance work and like that. They are gone. They disappeared about 2 years ago. And, do we have any records of what we've lost? It's going to be the little ones, obviously. But, do we know that?
I don't know how many have disappeared. I mean, definite glaciers have disappeared, completely disappeared, especially in the regions with smaller ice masses. One of the slides about the temperature increase per degree showed how many glaciers are projected to disappear by the end of the century. And that was almost, that was a huge number. But of course, what is left are then the bigger ones.
Thanks for your talk. I mean, this is I really enjoyed that. This is stuff. I'm a climate scientist as well, so I kind of, these are figures that I kind of know, but the images are just so striking. And some of the computer models and simulations you had of that glacier in Switzerland under different scenarios are so striking. I was wondering, is that available somewhere, and how can you make that as available as possible? Because in terms, this is the canary in the coal mine here, right? And the kind of visual impact of what you just showed is just so powerful that I kind of found myself, despite kind of knowing this stuff, like very moved by it. So I wondered is that available, and how you plan to kind of make it more available, those impacts and visual images?
Yeah. The talk is available on YouTube, as far as I understand, but I am all for free research and showing everything. So if any of you wants any of that material, I am happy to share it. I think the messages need to get out. I'm not protected about anything what we do here as a scientist. I am happy to share everything I have.
Your broader public and kind of cultural recognition and cognition, I do wonder, are you kind of directly speaking to, say, the ski industry, right? Just in that it's something that kind of, I don't know, a bunch of people, in minority, but still a bunch, connect with. And oh my goodness, there's just like, that just disappears, right?
Yeah, no, as part of this SROC IPCC report, there's a whole page about the impacts on skiing. I focus here on the glaciers because that is more than snow, but there is research on it, and it's nicely summarized in the IPCC SROC report.
Yeah. Hello, thank you very much for this presentation. I was wondering what would be the main recommendation you would ask policymakers to put forward to better anticipate those risks? Information sharing is one, and would you have any other suggestion? Thank you.
I mean, of course, the broader scheme is what I said, every degree warming matters. So limiting warming will keep more ice on land. I mean, that's sort of the basic message. But of course, you can also do mitigation and adaptation in local cases where the glaciers matter. And that has to be sort of decided on a local scale, what is possible. But the global picture is clear. I mean, the warmer it is, the more it melts. You can't, as it nicely summarized in that report, you can't negotiate with a melting point of ice.
Hello. So thank you very much for your presentation. And so just to follow the previous question, do you have any thought and recommendation about the management and maybe governance of the proglacial landscapes that appear after glacier retreats? So if we think that in a lot of countries already we have lost glacier, so it's a fact, and glaciers are going to disappear for a lot of regions, it's a fact. So if we are thinking about adaptation from now, looking at the future, and that we are going to lose more and more glacier, so maybe we have to do something in this place, thinking that we have mining industry, we have hydropower, we have tourism, we are local community. So do you have any thought on this topic?
Well, the deglaciation that is, of course, part of the mass retreat is a complex issue because in some cases it can lead to more destabilization and more hazards. In other cases, maybe beautiful lakes appear and it increases tourism. So it really is also on a case-by-case basis. One has to see the impacts, which can be negative and which can also be positive. Yeah.
So at the National Snow and Ice Data Center, where I'm at, we're involved in this GLIMS project, right, to try and get an inventory of what we've got in the world, right, and it's being combined with other data sources and things like that. But do we really have a good idea at this point of what we started with, say, like in 1980? What did we have, right, that we can really make an accurate assessment of what we've lost?
That's a very good question. Actually, the first global really in a global inventory was finished for just prior to the IPCC report, the Area 5 in 2012. That's the Runoff Glacier inventory. And before that, there was really, really good data in the GLIMS database, but the further you go back in time, the less there is. And the coverage before 2012 was about 40-50%. So it is very hard to really know how much area has been lost prior to these inventories.
Okay, thank you very much, Regine. Thank you everyone for joining. We're now closing this event. The next event starts at 1 p.m. and it will be on preservation of glaciers at 1.5 degrees. So welcome back later.